Hi, welcome to video on tuned amplifiers. So this is a very short video. We will see, okay, this is an amplifier with multiple tune circuits. So we have one tune circuit constituted by C1, L1, and of course the input impedance of the network as R1. And of course we have second tune circuit at the collector side, which is constituted to C2 and R2. And you can see there is a peculiar component which is RFC here in series with both the series bias resistance RB1, RB2. So these two are used to, as it is mentioned here, to avoid effect of this radio frequency choke will offer very high resistance for the AC signal, that is the incoming signal, the input signal, whereas it acts like a short circuit for the DC current. So this will not actually affect the biasing of this transistor at all, but this will stop loading the input stage of this tune circuit. So the input tune circuit stage, we have actually two tune circuits, one at the input and one at the output. And of course we have the major disadvantage in this type of multiple tuned amplifier, that the output is coupled to input through this coupling capacitor, which is a parasitic one. This is C mu. Suppose if the conditions are such that for a particular frequency, suppose if the loop gain happens to be equal to -1, which is actually the condition for oscillations, that is if it satisfies Berkeley criteria, this amplifier, instead of acting like a tuned amplifier, will start behaving like an oscillator, which is undesirable for any amplifiers. So such type of undesirable oscillations can be avoided eliminating this direct coupling from output to input. So that can be accomplished by having a different configuration for this multiple tune circuit. So this is one such configuration where we are trying to avoid the direct coupling from the output point to the input point using cascade configuration. If you can see here, this is a cascade configuration having C amplifier followed by CB amplifier. So this is a configuration C followed by CB. So this will actually, this is also having a two tune circuit, one at the input and one at the output. But major difference between the previous and this circuit is we don't have a coupling from the output point to the input point directly. So this will avoid the amplifier breaking into oscillations. So this is the biggest advantage. One more such configuration where you are trying to avoid the output with the input using a simple coupling capacitor now is avoided, because now it is passing through two transistors. So it is highly impossible to have this circuit breaking into oscillations. You can see now this is a CC amplifier where you are taking the output at the emitter. The output is applied to the second emitter and you are having the output taken at the collector, which is the CB configuration. Since you have a CC followed by CB, so this is a CB-CC configuration. Here also we have two different tune circuit deciding the tune frequency of two tune circuits. So depending on the type of tuning that is happening between the two circuit, as we can see here, this is a multi-tune circuit. You have one tune circuit realized using L1, C1, R1. Again L2, C2, R2 will decide the second one. If both the tune frequencies are same, if you can see here, this is the black one. Suppose if both the tune circuits at the input and output, if they have the same type of frequency response, that is if both of them are tuned to same frequency, you can see we end up with a overall frequency response which is much more steeper one. So this is much more having a larger Q compared to the previous one. You can see the larger bandwidth, the earlier bandwidth was larger. Now you can see the resultant bandwidth is lesser. If you can see, there is an expression for the resultant bandwidth, which is omega naught by Q and under root of 2 to the power of 1 over n minus 1. So this this factor, that is under root of 2 power 1 over n minus 1, happens to be the shrink factor or the shrinking factor, where n happens to be the number of tuned circuits you have, number of tune stages you have, whether it is 2 or 3. Now if you can see here, this is the bandwidth. So bandwidth is usually given by omega naught by q, and that will be shrinked by this much amount depending on what is the value of n. Suppose if n is equal to 1, where you have a single tune circuit, so then this bandwidth happens to be omega naught by q only. Suppose if the value of n increases beyond 1, then this starts reducing less than 1. In such case, we will going to have this bandwidth. You can see here, the black one has got larger bandwidth, and you can see the blue one has got a reduced bandwidth. So omega naught by q was the original bandwidth when n is equal to 1. You can see now this is the new bandwidth after multiplying this shrinking factor. This shrinking factor is due to the addition of more and more number of tune circuits. So this way we can able to get a higher Q circuit or a bandwidth of very small value. So if you have two tune circuits, both of them tuned to a single frequency, we call it as synchronous tuned amplifiers, meaning the values of L1 C1 R1 and L2 C2 R2 will be same, so that both of them can tune at a particular frequency. Both of them will give maximum output at a single frequency, which will result in this type of frequency response. And it is also possible that both tune circuits can be tuned to different frequencies, so which will result in something like this. You can see this is the response of individual circuits having omega naught 1, omega naught 2 as the two different tune frequencies of input and output stages. Overall response looks like this. In some cases, we may want to have a larger bandwidth. So in such case, we can go for this type of amplifier, where it is called as staggered tuned amplifier. So you have a set of frequencies over which you want to have maximum bandwidth. So that can be tuned using input and output stages. Now we can see the bandwidth of the resultant, again multi-stage tuned amplifier, will be slightly larger. Now the bandwidth of this type of staggered tuned amplifier is decided by what is the tune frequency of the two tuned amplifiers which are placed at different frequencies. Now this is in this case these values of first tune circuit is different from this one, so in such case we end up with a staggered tuned amplifier. The difference between synchronous tuned is we're going to have both the tune circuits tuned to same frequency. Here it is tuned for different frequencies. These are the individual responses of a staggered tune circuit. So individual responses will be identical. So we end up with a more sharper frequency response as the resultant one. So in the next case, it will be a more wider frequency response in the second one. So in case of staggered tune amplifiers.